Hello everyone, it's me, Aster, back with a new math video again this time. It's not about solving problems or any particular concept actually, more so about something I found, kind of like how I quote unquote found something about the flow function, but this time it's gonna be about something a lot cooler and something I'll probably get kind of flamed about. But I tried. It's not like I'm trying to show off something cool here. If anything, it's a cry for help, if anything. But I'm just gonna show you what I got regardless, because I think it's kind of cool, right? So here we go. I'll just go in the order of what I think would make the most sense, and not really the order in what I found it. But if you want to know that, I'll just put in the description somewhere. But yeah, so where it all begins is a circle, right? A circle, center O, and so what I wondered was basically that if you take a point on this circle, some point A, right, and if you like joint it through O to the opposite side, you're gonna get a you're gonna get a diameter, right? If you draw a line from here that passes through O, you're gonna get a diameter B, right? And considering the properties of a circle and everything, every point on a circle has only one diametrically opposite point to it. So A has only one B for it. A has only one diametrically opposite point, that is B. And say I took some point A2. Let's name this A1 for reference. A2 is gonna have only one B2, and A1 is B1, right? And you could draw points like these throughout the circle, any point that lies on it. And so I just wondered if if you take all the points, right, you make an ordered pair basically. A1 or unordered, frankly speaking, doesn't matter. A1 B1, A2 B2, A2 B2, and so on, like this. You're technically getting pairs, right? Each pair, this value represents a point, which is kind of ironic because ordered pairs are used to represent points or whatever. Right? So A1 is a point and B1 is a point, A2 is a point and B2 is a point. And the collection of all these points together is, by definition, going to be all the points on the circle, right? So I was wondering, this is 2, right? And this is 2 as well, and so on. You're just adding up pairs, right? There's like 2 sets in each pair, so it's going to be 2 plus 2 plus 2, so on. Wouldn't that really imply that number of points in a circle is even? Isn't that what it kind of implies? A1 B1 A2 B2, it's all a pair, right? I could divide this circle into 2 halves, like a semicircle like this, just for division sperm. That's for the sake of explaining it, right? Let's call this the master diameter or whatever you want to call it. This is marker with D. You could take any point from here to here, and you could connect it to any point on the semicircle on the other side. Okay, not any point, but yeah, you could draw a line that passes through the center, and you'd get only one point, P1, A1, P1, that pairs it up, right? So you could just say number of points on a circle is even, right? And let's say, by using proof of contradiction, that after all these pairs have been made, let's just draw something like this, some lines and all that, blah blah blah, just draw up some lines. We have all these points are connected and everything, and let's assume that the number of points in a circle is odd, because if something isn't even, it's odd, am I right? So let's just take some pointers there, it's odd, right? That would mean there's no other point anywhere else that you could just pair this up with, right? But then here's the thing though, a circle, it's like by definition, if you take any point on the circle itself, you should be able to connect it to the diametrically opposite point to it. So that either means that this special point we have, let's call it C, and everything else A1, A2, whatever, right? And this one is just P1, P2, so on, right? If we take this point C, by definition of our circle is either this point, and we are taking distinct points here, by the way, not just any points, but distinct points. C, right? If it's a distinct point, it is by definition of how a circle is, if you define it as a locus or something like that, I believe, I don't know. See, it's gonna have a point to it, let's just mark it as BC for the sake of it, right? Either that or it's not a distinct point, which means it's either A1 or something like that. So, proof by contradiction, I feel it would say that, yeah, the number of points on a circle is gonna be even. I know, you can make the argument that, hey, a circle, has an infinite number of points and, it's not finite. And maybe that's messing around with things. You can't just put even odd on infinity, because infinity just doesn't work like that. It's like got its own rules and shit. And yeah, that's fair. That's like an absolutely fair point to make. But all I'm just trying to say is just kind of think about it, right? Come on, it's all pairs that form it. So wouldn't it make sense to say that infinity is even? Now I've got all this down, and the thing is, actually, this was not the only thing that I found regarding this. Actually, before this entire thing that I found, this quote unquote proof that the number of points on a circle is even, I kind of got something similar to this, more so demonstrating this behavior in a circle than actually proving this. But I feel like I might as well show it because it could serve a good basis, right? Take any regular polygon, right? You take a triangle, a square, a pentagon. You know what? Let's just use different colors for this. That'd be fun. So, say you take a triangle and then a square and then a pentagon, then a hexagon, and so on. Anyways, so you get the point, right? It's all like this. I've marked the odd number sided ones in red and the even number sided ones in green. Right. So one thing you would notice is, let's take the pentagon and the hexagon for example, because I don't know, hexagons are cool. Right. So let's just take this. Take the pentagon with even number of sides and you join up all of the diagonals, right? You join up all the diagonals. You're gonna see that none of the diagonals exactly intersect at the apothem of the pentagon itself. If you want to define the apothem is going to be any point inside a polygon that is an even distance away from all of the sides in the polygon itself. Actually, all the points, my bad. All the points in the circle. So this is equal to this, is equal to this, is equal to this, is equal to this. This distance is even. And how the apothem is formed basically is by constructing the the perpendicular bisectors of all of the sides and like marking the intersection point. That's why you only get the apothem for a regular polygon. If you try for another kind of polygon, yeah, you're not gonna have much luck with that. It could be possible, could be not, right? You can't really say much. But then for a regular polygon, it's absolutely a shot. So you construct this and that, and it's kind of on the basis of how you can construct a unique circle with any three points, right? You construct the perpendicular bisectors and you make them intersect, and that's the center. That's how you get the circle. But right, so you can see the apothem here, it does not intersect over here, but for the even-sided ones such as the hexagon, it perfectly intersects at the apothem itself, right? So this is the apothem and it perfectly intersects here. And so maybe it's going on for like odd number of sides, it's not like this, even number of sides, it's not like that, because it's like a behavior. Maybe we've seen in small sides, maybe for bigger sides it's different. Well, so what we're gonna do right now is we're gonna prove that it'll never really touch the apothem, the diagonal's intersection point, for odd number of sides, but it will for even number of sides. So let's prove that, right? So take any n-gon, right? Let's take the hexagon itself. Let's take the hexagon itself because that's chill, right? You take the hexagon and you mark the apothem for this, right? And you connect the apothem with all of the sides. So what we could do is, what we really want to prove is that any regular polygon has at least one pair or two diagonals two diagonals that intersect at the apothem A. Let's mark the apothem as A, right? So we could do this by various methods, but the method I did it with was basically taking these lines that you're connecting the apothem with the sides with and trying to prove that these two are straight lines. So how we're going to do that is basically see, for the hexagon, for example, the special thing about a hexagon is that the diagonals divided into 6 congruent triangles. These diagonals basically, not these ones. They don't do that. But yeah, so taking this, we get that it's divided into 6 parts, right? And since we know that these are congruent triangles, that means this angle is equal to this angle, 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 and this is equal to this angle, right? And it's a full circle, and we have 6 angles here. So it's going to be 360 by 6 is equal to 60, right? And these are equilateral, and since this is equal to this, that means this is an isosceles triangle. So 60, 60, 60, it's equilateral triangles that are all congruent to each other. Nice, perfection level of perfection, right? So we could take these angles, right? This like a single angle on here for any n-gon, regular n-gon, where n is even. The angle, or any n-gon actually, the formula is not specific to this. The angle is gonna equal 360 by n, right? So what can we take from this information, right? This angle is 360 by n. Here, let's just assume this is an n-gon and not a hexagon. Okay, 360 by n, we have that here, right? And say we could use this data to derive perhaps that this line is straight and this line is straight. So what do we need to do for that? We need to prove that the angles between this and this add up to 180. And this is 360 by n, 360 by n, 360 by n, 60 by n, plus 360 by n over here. That's what it's going to be. So 360 by n, right? How many times? Since this is a hexagon, 1, 2, 3, 3 times. And hexagon, 6 such angles or sides or whatever, 6 points we'll take for this reference. So 3 by 6 by 2. So, we could just put that ellipsis here and we could go down, and yeah. So basically what we're going to have to do is 360 by n times n by 2. N cancels out, and this is going to become 180, right? Now that we've proven it's 180, we've proven basically that it's going to be even throughout, right? It's going to be a straight line. And similarly, you can prove that this is also a straight line. So, and since a straight line that connects any 2 points on a polygon is basically its diagonal, we've proven that we have a pair of diagonals that actually intersect at the apothem, right? Now, why can't we do this for odd-sided figures, you might ask? So let's construct the pentagon real quick, right? Right, we construct the apothem and everything, and we try to use this proof, right? 360 by n times 3 times n by 2. That's what you want to do here. But when you draw the lines, you notice something, don't you? The thing is, there's 2 uneven paths this could take, because think about it, n by 2, say we've taken the pentagon for some reason, right? As the example, n by 2, n is equal to 5, right? The number of points or the number of angles, whatever, is all the same. 2.5, right? You cannot really have 2.5 number of angles. You can have either 2 angles by taking the floor. You could take the floor of 2.5, you could get 2. Or you could take 3 angles by taking the ceiling of 2.5, which is 3, right? So you could take either of those, right? And you could basically, and even then, if you do 360 by n times 2, wait, this will become 5, let's just substitute that in, times 2, you're gonna get 144 degrees. And if you take it as 360 by 5 times 3, you're gonna get 216. Neither of those which are equal to 180, which means no matter how you take it, you're not gonna get a straight line out of these, right? So for even values, the angle you're going to get, even values, it's always going to be basically by taking this process 360 by n times n by 2, you're going to get 180 degrees. However, for odd values, if you take two cases, because in this case because you're doing by 2, odd numbers by 2, you're only going to get 2.5, you're only going to get some, if you take its floor, it's going to be x minus 0.5, or if you take x to be the number of sides itself, by 2, you could either get x by 2 minus 0.5, or if you take the ceiling, you're going to get x by 2 plus 0.5, right? So you're basically you can write this out down as C16 times n by n times x plus or minus 1 by 2. This is n, my bad, right? So this is basically going to become 180 into 1 plus or minus 1 by n, basic. But yeah, it kind of shows how for any odd values of n here, it's not gonna work out well, and it's just gonna be different from 180 by a certain factor, right? Now here's the thing with circles, kind of, right? With the circle we've already seen from the last part of the video that you connect these up, right? You're going to connect the points, all of them pass through the center, right? And the center, if you take a circle to be an infinitygon is defined as any polygon with an infinite number of sides, so infinite number of points or sides. Points would be more appropriate for our example, vertices to be exact, but points, whatever, right? You could take the center to kind of be the apothem for the circle itself, and guess what, you could take any two diameters of the circle and they would always intersect at the center by definition, right? Because a diameter is defined as any line drawn from the point that passes through the center to the other point, right? Nothing else really matters there. So yeah, you could say it's even there, right? So 180, it is a straight line, it's 180. But here's the thing though, odd, right? Say I take if I take the limit of this, right? 180 or 1 plus or minus 1 by n, and I take the limit as n goes to infinity, that this would just become 180 degrees, right? We can take that, absolutely. But then yeah, so I got this and I was kind of just like, okay, so yeah, I disproved everything. But then I just thought up of this previous segment over here after that, and I was kind of just like, whoa, there's something to this, right? And what I feel like is happening, kind of, this is just my own terrible speculation, is that infinity is just kind of pushing it from being odd to even. It's just kind of merging the point into this, so it's like becoming a diameter. It's kind of like the difference gets so minuscule, it gets so small as the limit goes to infinity, because 1 by infinity goes to 0, right? The difference gets so minuscule, it's just infinity is like, who cares, it's just 1 point, right? Just 1 point, boom, 2 points, 1 point, yeah. It goes from odd to even. It's kind of just pushing against it being odd, and it turns it kind of even, if you know what I mean, right? If there's any flaws with my logic and anything, absolutely tell me what they are, pull it through, right? I really do need it, right? The comment section's always open for that. And now here's the third thing I kind of wanted to show about this. Something with real numbers, because it's the number line and everything in the circle and all the points associated with it, all that nonsense, right? I was kind of thinking, hey, what if we try something with the real numbers over here? So I'll draw the real number line. We'll go from 0 to 1, okay? Right. So all these real numbers over here. So I was just wondering, hey, what if I try to determine the number of points between 0 and 1? It'd be real numbers. And my hypothesis was that this would be odd as well, even as well, because you can just associate the points on the real number as the points of a circle, right? You can just associate that. Was what I went and think about this. But then I kind of noticed something else actually occurring, right? So between 0 and 1, we'll generalize this example later, right? You can take any value x such that it belongs to 0 and 1 included, you know, and the value 1 minus x would also belong to 0 and 1. For example, you substitute in 0 here, you're gonna get 1. You substitute in 1 here, you're gonna get 0. You take in 0.23 for example, you're gonna get 0.77, right? So you, and these are all going to be distinct points, mind you. X and 1 minus x will always be distinct, so no repetition of points, right? So you can make a pairs like these of 0 and 1 to 0.1 to 0.9 and so on, basically for the pair of x 1 minus x, right? You could make up this pair and everything, so it'll be even then, right? But then here's the catch: distinct points. That's where the catch comes in. Take the value x is equal to 0.5, the midpoint of this, right? 0.5, you put it into 1 minus x, you'll still get 0.5, right? And we're taking distinct points over here, so you cannot really make a pair of 0.5 and 0.5, as they're not two distinct points, they are literally the same points here. So we have this entire pair plus this one element of 0.5, right? And so if we take the whole same number of points, 2 plus 2 plus 2 logic over here, we'd get that this entire thing is even, right? But then here's the plus 1 element. We're talking about the size of this entire set, right? And even plus odd, as we all know, is odd. So it'll just be even plus 1 becomes odd, right? So even plus 1, there's 1 more than even, and it becomes odd, right? So I thought that was kind of cool. I was really trying to see where I could just change this around or something to try to make it even, but nothing really worked, so that I could make it fit in with the circle and everything. But I was kind of playing around with, maybe what if I use 0.5000001 and 0.49 factorial, because they're technically 0.5 and everything like that, distinct, non-distinct, everything. And I was thinking about that, but doesn't work out, right? And frankly speaking, this being odd works out more with the circle idea than you think. I'll come to that in a second. But with this, I did think of something cool, right? Something new. So if you do like take the line, you take any point 0.5 on it, the 0.5 is going to be like 0.501, 0.409, but then there's also going to be values like 0.50002, or values like 0.499999, and at the infinite and 8, right? So but all of these are, technically speaking, because they're so infinitely small, they're all 0.5. So what if you took a little circle like this that holds all these values, like a little keychain of sorts, holding all the 0.5 values, and the main one you use is 0.5. You could do the same with 0.2 and 0.98, for example, whatever, right? You can make little chains like this, and 0 and 1 would have their own chains too, like this, right? Okay, so keep this in the back of your mind for a second. Right, I told you how this will work out with the circle, right? So let's just snip away a little bit. We take the line 0 and 1 only, separate it from the rest of the line, and say we connect these both ends of the line together, So you take it and just turn it to a circle, you join the two end points, right? Very common thing to do with string and everything. I feel like we've all done that in grade school. So you join this together, and 0 and 1 merge to form a point, right? So you have this odd number of points, okay? You have this odd number of points, but then these two merge to become 1 point on its own. So wait, just let me show with that. 0 1, it merges together, and on the other end you're gonna have 0.5, right? So you're gonna take this out of this set. We're just gonna pull this out now. So you're gonna be left with say 0, 0 0.1, 0 0.9, and this entire pair and so on. Everything else just works out fine and everything, and you have this little set x1 minus x. And these points don't really merge together because you're not connecting these 2 points specifically. They're in their own respective positions. I'll add on if I want to draw it right now. But yeah, but then you're gonna have this plus 0.5, and then this another point that's in a bit of a superposition right now, right? It's kind of just going like, am I 0 or 1? It's kind of in a silly situation like that, 0 or 1. Regardless, maybe I'll just draw a slash there. 0 or 1. It does not know where it exactly is, right? What we've basically done is merge 2 points into one. We basically took the endpoint 0 and 1 and merged them into the superposition of being 0 or 1. Quantum computer style or something. My god, why am I like this? Anyways, so you have this. It's still gonna be even regardless. This entire thing is gonna be even because again we have pairs over here, right? But then we have this 0.5. So let's just label everything again. Even. Then this is plus 1. And then there's this plus 1 as well. This extra point over here. So you get even plus 1 plus 1. Which becomes even plus 2. And 2 is an even number. So it's going to be even again. So when you take the number line itself, 0 to 1, or I'll put the general formula soon enough. 0 to 1, it's odd, right? Because every line has a midpoint, right, which does not have a corresponding point equal to some sort, because distinct points, right, it's going to be odd. But you join it to make it a circle, right? Superposition, yeah, the midpoint, it's even now. How cool is that? It just kind of makes sense, right? Again, I know it's the whole infinity doesn't work like that and everything, just completely fair, but it's kind of like, think about it. It kind of does make sense though, doesn't it? Right? So there's this thing, right? And say you connected this little line together like this, you joined these circles together, you kind of get like a little you kind of get like a donut made out of these circles. My goodness, my drawing is horrible. But yeah, you'll get these little drawings of distinct circles like this, right? You'll make a little donut out of it. But here's the thing though, they technically speaking slowly transition from one value, right? So I have 0.5 here and 0.6. The jump wouldn't just be sudden, right? It is slowly transition back into 0.6. So I suppose it'd make more like a spiral that folds in on itself. Okay, not folds in on itself, I don't know what it's called, but yeah, you'd form a spiral that forms a donut like this together, a spiral kind of donut, right? And maybe this seems like way too far beyond projection from me, but people that know what I've been doing, what I've been working on for the past couple of years, they're gonna look at this and they'll know exactly what I'm talking about. So I'm just keeping in this in for those people. Yeah, right, I love every one of you. So, the little donut thing, that's fun, but so yeah, that's the entire thing I kind of got, right? I know, infinity does not behave like that and everything, it's odd, I get it, even odd, it just doesn't how infinity works. I get that explanation, but it's just kind of, think about it, it kind of makes sense, doesn't it? Because it's kind of just like, hey, maybe it works out. I'm not trying to imply anything or anything like I've made a great discovery, because nah, I ain't that guy. But then it's just kind of, maybe it's cool, maybe it is something somewhere, right? Just something to think about, something that could lead to something better is all I'm trying to say. Oh yeah, I got sidelined, my bad. We're supposed to prove this for the general case, right? Okay, here we go. So take some value y and some value y plus alpha. Okay, so it could be negative, positive, y could be any integer or real number you could take, frankly speaking, doesn't matter, right? So you take this little set we have here of numbers. So we need to, so let's say we have some value x again that lies between y and y plus alpha, right? So, we need another value that would also lie between y plus y and y plus alpha. And, I'm not gonna go into the nitty gritty of how I derived this because I did not derive this. I just got it through trial and error. But it's gonna be 2y plus alpha minus x. Minus x belongs to y plus alpha, right? That's what you're gonna get here. Okay, so we have this, and again you form this pair 2y plus alpha minus x. You just form this little pair. You know what? Maybe I just want to use a little notation today. Okay, never mind. So you form this little pair and everything. You have these pairs all lined up together in the cute little section. What is wrong? Right, you have this all together, but then we have to find the point that's between them, right? And to basically find that, you just have to equate these together. X is equal to 2y plus alpha minus x. Transpose this to the other side, you're gonna get 2x is equal to 2y plus alpha, or basically x is equal to y plus alpha by 2. So this basically proves that there's always going to be one value where there's going to be a midpoint, which is y plus alpha by 2, which makes sense. Right. So it's basically proved that you're going to have one common point where you cannot really form a pair of distinct points, because y plus alpha by 2 is equal to y plus alpha by 2, and you can only form an ordered pair here if the two values are not equal. They're equally opposite, but then they are the same value. You cannot form a pair here. So what's basically going to happen, you have this entire thing plus your little set of y plus alpha by 2. I apologize if I used the wrong brackets. My brain is not working right now. But so yeah, this is the entire thing. It's been bugging me for a couple of weeks during my finals, because that's when my brain decides to do this to me. But yeah, I just thought this was really cool and something I wanted to show, and I really want a feedback on this, because I feel like I'm probably missing something here, and I would love to learn what I've gotten wrong over here, and I'd low-key kind of appreciate it if it's in something like it's infinity. That's not how it works. That'd be kind of cool, something more so I can understand about infinity itself. Any sort of criticisms over this would be massively helpful. And thanks for watching me yap about random nonsense. I appreciate it. But yeah, any helpful advice or anything you want to give me, I 100% appreciate it. Do it through the comment section. I love y'all. Thank you.